And we'll start by just sketching out what the problem actually involves. It's a piston cylinder that initially contains hexane in both the vapor and the liquid phases. So 0.2 of a mole of vapor hexane and 0.8 of a mole of liquid hexane. And then we're going to add some water to it at constant pressure. And we want to know what's going to happen to the phase equilibrium. To analyze the situation, first we'll look at what happens to the hexane phase equilibrium. All right, and so we know that if we have two phases, which is still not determined, that the fugacity of the hexane in the vapor phase will be equal to the fugacity of the hexane in the liquid phase. The fugacity of hexane in the vapor phase for an ideal gas, which we expect at this low pressure, should be equal to just the partial pressure of hexane. And the fugacity in the liquid phase for pure component hexane, again, this is at low pressure, is just equal to the saturation pressure of hexane. Okay, and so this is the relationship that describes the equilibrium. Partial pressure of hexane is equal to the saturation pressure of hexane, which, based on the initial problem statement, we were told that we began at 1 atmosphere. Right, and so we know that that pressure is 1 atmosphere, and the saturation pressure is therefore 1 atmosphere. Okay, so now let's look at the new situation. All right, and so now we've added water, and water will exert some vapor pressure. And so the 1 atmosphere that is the constant pressure, we know it's the total pressure. That has to be equal to the partial pressure of water plus the partial pressure of hexane. But we know that if we have vapor-liquid equilibrium, that the partial pressure of hexane is 1 atmosphere. All right, so this is a violation of the equilibrium relationship. And instead, the partial pressure of hexane, because there's going to be some water present, is going to have to be less than the saturation pressure of hexane. All right, so since the fugacity of the vapor phase is lower than the fugacity of the liquid, all of the liquid hexane will evaporate. Now for water, we can write a similar relationship that the fugacity of vapor phase water is equal to the partial pressure of vapor phase water, which is equal to the saturation pressure of water at 60 degrees C, right, the temperature in the problem statement. Right, the saturation pressure of water at 60 degrees C is less than 1 atmosphere, right, significantly less. And so it's possible that equality that's written right above, that 1 atmosphere is equal to the partial pressure of water plus the partial pressure of hexane, can be satisfied. All right, but it's actually not clear whether two phases for water exist or not. All right, so it actually depends on such parameters as the size of the container and the relative amount of water for that size. But if, when you add the water, the partial pressure can be equal to the vapor pressure of water, right, then we'll have two phases, and we'll have liquid phase that's just water and a vapor phase contains both water and hexane. Or it's possible that we'll have just a vapor phase that contains both water and hexane, depending on whether that equality, 1 atmosphere equals partial pressure of water plus partial pressure of hexane, can hold when the pressure of water is equal to the saturation pressure of water. Right, so we just don't have enough information to solve that problem.